My name is Jeremy Forn with Blue Flag Consulting. My background is data analytics in public transit, more specifically subway systems. And I'm really excited to share with you one of the challenges I came across in this space and how Elasticsearch allowed us to solve some of these challenges in real time. So to do that, first I'm going to share some of the challenges subway operators face, how data that's becoming available can be used to inform those decisions, how those decisions can be based on journey analytics from systems like graph databases or Elasticsearch. I'm going to build both of those in this talk. And from those systems, what can we get? What is the value and the actions we can take? And then I'm going to wrap that all up in a conclusion. And if it seems like I'm talking fast, it's because they said if I can do this in under 10 minutes, I can spend the weekend at Shy Bannon's guest suite. So that's why I'll be speaking a little fast. This is the Toronto subway system. If you live in a major city, you'll know that if there's a subway, it is the lifeblood. And if it stops operating effectively, the whole city sort of seizes up. And so the subway operators who run these subway networks are constantly trying to keep this operating while also moving people as effectively and efficiently as possible without sacrificing safety. And to do that, there are some challenges. You may be dealing with things like congestion. So many people are in a subway station that the platforms become unsafe and you need to turn people away. Or you're a city like New York where you're trying to keep this operating 24/7 with the ability to just shut everything down while you do some repairs. Or there's unforeseen disruptions like weather or malfunctioning equipment, which causes irregular traffic patterns. And this is even harder in Toronto, where the Toronto Raptors have been winning an NBA championship every 4 years on average since 2018, which just means there's a lot of parades and celebrations going on. So these are some of the challenges you have, and these might be similar to systems that you yourself might manage: congestion, operations, disruptions. And you won't be surprised to know that there are constraints that these rail operators have to deal with. Maybe legacy infrastructure. These stations have been around for 100 plus years. Things like resource constraints. So there may be a very good solution to the problem you're trying to address, but you just don't have the resources to deploy it. And finally, maybe the use case you have is unique. So a lot of subways are as unique as the cities they're in, which limits the amount of options that may be applicable to you. So if you have these constraints and you're trying to run this very vital service, your limited options mean you need to make better decisions. And the key to making good decisions is good data. And if you're going to improve how people get around a city, you need to measure how they're doing it. Now, it may surprise you to find out that a lot of subway operators don't have access to how people are actually using the subway network or getting from A to B. You might have turnstile data, which could show where somebody taps in and taps out. But what you really want, what's really important, is the path they took along the way. So did they go one route or the other? The reason this is so important is if you want to shut down a station, then you need to know how many people will be affected by that. And you need to know the routes that go through it. This is where you start to get into journey analytics. And as more and more subway operators are making public Wi-Fi available at platforms, the Wi-Fi data can be used to derive these journey analytics. So I'm going to imagine you have Wi-Fi in the subway. There's going to be hundreds of millions of events as your riders are associating and disassociating to the access points in the Wi-Fi network along their route. So what I've done here is distill down what some of those records might look like from hundreds of millions to sort of one journey. And you'll see there's timestamp information when a device may be entered a subway or exited. And you can see here, this is a trip. We've clustered together these events into a trip. You see somebody started at Christie and ended at Union. And in order to decide, which route they took, in that the stations that we saw their device along the way, it's fairly intuitive to discern that. You can see, well, if we saw them at Museum, they had to go, this route as opposed to the other, maybe route A versus route B. So now we're faced with a new challenge. Which is, even though it's intuitive to us, how do we come up with an algorithm so that this can be processed at scale in near real time? And to do that, we'll turn to graph theory. Now, graph theory is a branch of math that models relationships between different nodes and edges, and was originally developed to describe the 6 degrees of Kevin Bacon, or Bacon's law, if you will. In graph theory, there is a subset, which is pathfinding, which is a set of algorithms inside graph theory to calculate things like the journey length and time and best route. And so what I'm going to do now is build out an entire graph database of the Toronto subway system. So using Neo4j, Neo4j is sort of one of the more popular graph databases. And so you can see I've already started the subway TTC, but there's no nodes or edges or stations or anything like that in it. So I'm going to create a new Python project. I'm going to try and use Copilot to write as much of this as possible for me. So let's enable Copilot and see where this gets us. Okay, this is looking pretty good. It picked up on the Toronto subway stations. These are the edges between them. We have the actual stations here, some information, some formatting, and then it looks like the actual queries to build those assets inside of Neo4j. So let's go ahead and run this. Now that we run this, let's have a look, see what we got. So you can see here's the Toronto subway system. If I zoom in a bit, here are the different stations along the way and how they're connected to each other. Now let's go back to that query we had before and try to see the routes between Union and Christie. So if I was going from Christie to Union, show me the shortest path. Here's what that query looks like in Neo4j. And you can see, okay, it's kind of clear that I have to decide between these two paths. So now let's take the query again and add the intermittent stations. So this is where we might have seen them with the Wi-Fi data at Museum or Bathurst. You'll see that it's now becoming a little clunky because we need to add all of this sort of other if statements on top of our query to filter out anything else. But here you go, we have our the path that this device we observed. Okay, so this gets us pretty close to solving this problem, but there's a few shortcomings. The first being the query language is pretty challenging to work with. There's a lot of different ways of solving these problems, and there's not a lot of consensus in the Cypher query of how to do this efficiently. But really, the real problem is scaling. When you go from a subway network like Toronto with 70-odd stations to something like New York or London with 400 plus stations, the amount of computation to determine the path goes up exponentially, right? This starts to become cost prohibitive if you're looking to make this a real-time solution to give you those path findings, right? Detect which path. And it's also hard to integrate into existing it may be hard to integrate into your existing pipeline, as you'll need to build out some APIs to talk to this. The client libraries are a little bit clunky as well. So let's do this again, but what if we think about this instead of a computational problem as a search problem? You can imagine there is a finite total amount of routes that exist in any subway system to get you from any possible station to any other possible station. And what we're going to do is just take and calculate every single one of them by brute force and push them into an elastic index. If we do that, we no longer are constrained by resources, computational resources. We can just do a search. We're searching for the routes that match the criteria in our query, right? Let's go ahead and build this out in Elasticsearch now. So using Copilot again, let's see how close that gets us. We'll go ahead and enable it. And now it looks like it's done a pretty good job of building out the stations and edges again. And now what we'll do is iterate through every possible station and all routes in between them. And every time we do that, we'll generate a route with an ID, and we'll push that ID into Elasticsearch. Once that's done, we'll go ahead and pop over to Cabana, where we'll drop into our dev tools. And let's see how many of these routes in the Toronto subway system we were able to generate. So if we look at our routes, we'll see there's 9,100, which is right, and then just under a meg in terms of primary storage, which is pretty cool. If we run a search, we can see that we have an ID, we have a start station, end station, and the intermittent stations in one of these routes or paths. So let's go back to our search before with Christian Union and see where we get. We see we have two paths here. And then if we do this again and introduce the museum as an intermittent station, we now have a station ID specific and based on the data we observed from the Wi-Fi network. Now, if we're looking at doing this in Elasticsearch, you'll see the query is much simpler, much more intuitive. We have our start station, end station, and any sort of intermittent stations along the path. Scaling becomes a lot simpler. This has gone from an exponential requirement to linear. If you want to do something like 1 billion possible routes, that's as simple as a 3-node cluster in Elastic, 3 shards spread across 3 nodes, and you'll know you can still get millisecond query response time, which is really huge. Integration's a lot easier. Elastic has that API interface to the database already, so that's one less step. And then there's a lot of rich integration client libraries and things like that. Okay, so getting back to the rail operators, what does this provide them? Like having this journey analytics data available to them, what does that do? Well, first, as you collect the route information, you start to create empirical data, which allows you to start making predictions about how the decisions you make will impact riders, right? So you can start making better predictions. And when you're making better predictions, it starts to allow you to make better plans, right? And those plans can be optimized for things like, I want to reduce the total amount of delays, or I want to reduce the amount of riders that are affected, right? Now, as your planning gets better, you can then start notifying customers with signage, or maybe even directly through smart notifications that say, this station will be shut down, which is a route we know you may take, right? And you can only do that if you have that sort of journey analytics path detection, right? And as you're notifying, if you can notify riders, then it means you can nudge them, right? And nudging means means to incentivize them to do things like maybe leave earlier or leave later, avoid rush hour. You can say things like, hey, we can provide a discount on your fare if you wait till after 6. Right? Now, this might not seem like a lot, but when you're dealing with tens of millions of riders a day in a large subway network, that can have a huge cascading effect on things like congestion. Or if you can notify people in real time, you can mitigate disruptions as they cascade across the subway network. So bring it all back now to our conclusion. As a subway operator, you have to face these very popular sort of challenges: congestion, ongoing operations, and unforeseen disruptions. And with journey analytics, that's really the data and the insights to understand how to mitigate or adapt to those challenges. And to do that, you need to be able to do path detection and journey analytics. And getting that information, having that available, being armed with that, allows you to do things, allows the rail operator to do things like predict, plan, rider notifications, and behavior nudging, and continuously iterating through that, just making the experience better for everyone over time. So thank you so much. That was my time. Jeremy Thorne. I'm with Blue Flag Consulting. We're a data and cloud consulting shop. These are the kind of challenges and optimizations that we love tackling and sinking our teeth into. Thank you to Elasticsearch for allowing me to talk, and we'll see you later.